Together, Gabversity, where facts don't care about your feelings. Let us begin with subspaces. We spoke about yesterday having a vector space, and we said, for example, that this three-dimensional is a vector space. You could say that. You could say that that is x, and that's y, and that's z into the third dimension. Now, I got 0 people on YouTube. I'm excited about this. Alrighty, so how do we make a subspace? Well, we got to make sure that it also fits all of the axioms. Now, the good thing about subspace is that you only have to test 2 of the axioms that we did yesterday. Does anyone remember the ones from yesterday? We had commutativity, we had inverse, we had it's closed under addition, closed under scalar multiplication. What does that even mean? It means that you can't escape. So if you were to take a subspace, let's say that, let's say I took this subspace, right? Here is 2 dimensions, and I said I wanted to carve a space out of this, which is just this section here. Well, here's a problem. If I have a point here and I add, another vector, I'm going to end up here. And so I'm going to end up outside the space. So this is not a subspace. Not a subspace. Can't be a space. Okay, it means it can't be a place in which you move. It breaks down. It makes no sense. All right. So it's the same with that's why, for example, the universe at the moment, for us at least, is closed. There is no way out of the universe. It doesn't even make sense to be what's outside, right? It's sort of like, like the Simpsons live in their cartoon. There's no way they can pop out into the third dimension. Doesn't matter where they go, they're always stuck within that world. And that's really looked like physics. Yes, well, physics can be a subset of maths in many ways, but this is just pure maths and pure logic, my friend. Alrighty. So here we go. Let's say that we have an infinite 3-dimensional space, which is right here. Now what we could do, we can take a 2-dimensional slice of this, sort of like toast or something. You take a slice of that, let's say we take, how do I do this? We'll take it at point 0. So does anyone know how to do a slice? I'm trying to do a slice, or maybe I can do a slice out here. YouTube isn't, so bad luck for YouTube. Alrighty, so this is an infinite space, and we can call that 2 dimensions here, and it just goes on forever. Okay. So there's no way out of this space. If you're at this point and you add 3 steps this way, you're still in this plane. If you add 3 steps this way, you're still in this plane. If you multiply this by 3, then it'll be up here, still in this plane. You can't get out of the plane. That's called being closed. So in other words, if you have a definition of a certain idea of logic that works in a certain number of dimensions, it's not going to get out of that. If it can get out of that, then you are not incorporating the whole topic you want to talk about. One of those, I thought physics calculate different dimensions. Yeah, this is math. This is abstract math, so it's a lot deeper than that. If you watch it's hard to follow unless you're watching the last 10 lectures that I've done on logic of maths. But if you go back and watch them after this, then this will probably make a bit more sense. Because what we're trying to do is figure out why anything is anything. I'm leading up to the next, within the next few lectures, we're going to get to how to prove stuff. What does it actually mean to prove anything? Don't forget, man, if any regulars are here, jump onto YouTube at GabSmacked, hit the like and subscribe. We'll try and get up to 1,000 subscribers. We're trying to. Alrighty. So it's easy to test in 2 or 3 dimensions, because all you have to do is say, well, here is my plane, all right? If I'm here, if I add 2 spaces here, I'm still on the plane. Anywhere I go, there, here, there, I'm always in the plane, whatever happens. If I multiply it, I'm still in the plane. So I can't leave this plane. Therefore, we know that this is closed. You cannot escape it. All right? And like us, we can't escape our universe. All right. So what is the point of that? The point is that when we deal with things with higher dimensions that we can't draw. So look at this one, for example. If we're going to deal with R4, that's 4 dimensions. How about R16, if we're dealing with 16 dimensions? We can't understand that in our heads, so we have to use the most highest resolution version of logic that we have. And that is what I just showed you in picture. But now we're going to do it in mathematical writing, that's what allows us to see all these high dimensions. So let's go. What do we got here? Let me show you one. Okay, so we're going to say that we have a subset. Okay, let's just call it W is a subset of some vector space. So you could say two-dimensional space is a subset of three-dimensional space, for example. Right, and that's not always the case, but let's just say that. Okay, it's closed under addition and scalar multiplication if we say that we have a point here, W1, that exists in this subspace. If we multiply that by some number R, which is an element of the real numbers, so like by 2 or by 3 or by a million or whatever, then we're going to get, let's just say W1R, right? And then this has to be a subset of the space. It has to be. That is the first thing. And we said that just now, we drew it. I said if you take 2 steps forward, back, sideways, you're still in that two-dimensional plane. That's what we're saying here, but this is across an abstract amount of dimensions. Okay, the next one is that we have to say that we have 2 points here, W1 and W2. If we add them together, let's just call it, W3, that has to be a subset of the subspace. So as long as these two things happen, okay, that is the mathematical definition of what we just drew. So this one here, if you take steps forwards and backwards anywhere, that one here, so that plus another one, or if you multiply it. So, if you say, I'm going to multiply my steps by 10, so it becomes 30 steps, you're still in the same, call it universe, then that means it's closed. Here is an interesting thing. It's very, very difficult to find any conclusive proof when your argument is not encased. Supernova, long time. If your argument is not encased within solving for a variable, even deeper than that, we're even defining what a variable even is. That's what we're getting to. We're going to get to what that even means. So I'll show you, what does it mean to have a line? Hey, good to see you again, my dear. What does it mean to have a line? I'm going to give you a definition of a line right now. Okay, so let me find a good one. I had a really good one here the other day. I want to share it with you guys. Damn you. Here we go. Okay. Let's say we have a non-zero vector v. Now this could be a two-dimensional vector. So let's just say that the vector is here. Okay, we're going to call that v. What is a line? The definition of a line in this case is, where did I go? All right, it's going to be an infinite amount of multiples of RV. So you could have v, and then you could have RV, which becomes this, because that's the whole thing is RV. Okay, and then you could have another one, which would be like a R2V. So the line is a combination of all of those, and you could call that RV, right, equals a line. Now, what's the point of actually doing this stuff? Well, because once we deal in multiple dimensions, how do we know we have a line? How do we know we have a line in 4 dimensions? Right? Well, then, if that's the case, what we do is we find a vector in 4 dimensions. So we find this 4-dimensional vector, okay, in 4 dimensions. And then if we want to say the 4-dimensional line will be R4 by V, okay? So that's how you would look at that. Actually, that wouldn't be a line, that would be a hyper 4-dimensional object. So that's what I mean. We're turning it from a line into a 4-dimensional object. If we want to get the volume of the universe in 4 dimensions, we're going to need this type of logic. And the thing is, this is not to calculate the stuff. This is to even know that you're doing the right thing. It's like we're living in the dark and we can't use our own senses to see what's going on outside of 3 dimensions or even 4. We have to start using logic to try and navigate what the hell's going on. Alrighty, so I'm going to give you an example. Here's one. Ooh, what have I got here? This is a really hard one. If you haven't done advanced maths, this one won't make any sense, but I really like this one. Alright, let's start with this. A set of all functions. So we have a set of all functions, f of x, and we just did functions, if you guys remember, if you go back 4 lectures, roughly. Okay, we're going to call that s. Okay, f of x on, okay, and we got 0, 1, okay, such that, okay, such that the derivative, the second derivative, okay, plus e to the power of x of the first derivative minus x by just the function equals 0. I don't know if that's coming out, okay? So you might have something that behaves in this universe. So this hypothetical abstract universe is all warped and twisted. So if you want to go in a straight line is going to mean a different thing in here. But we firstly have to know if this is even a valid universe. Is this a theoretical universe that could exist in in another alternate universe? And what you do is you have to do the two things. You have to say, well, if that's a set of the functions here, then the first thing we have to do is we have to check if you can add two functions, and you're still stuck in the same universe, remember? And the other one is you have to multiply the function by some number and you're still stuck in the same universe. They're the two things you have to test every time to know if you're dealing with a proper universe. All right, and when I say universe, that's not the real word. The real word is a vector space, but I'm just calling it universe to make it easy, but it's actually a vector space. Alrighty, here's one. Here's one that doesn't fit. And I'm going to draw it for you because it's only 2 dimensions, so it's easier. I'm going to start with the maths, and then I'm going to draw it for you as well, and then you can see what the maths is actually doing. All right, have a look at this. R2 plus. That means 2-dimensional number line, vector space, exactly. 2-dimensional number line, and it's only positive. So if I was to draw that, here's the 2-dimensional number line, it's only this section, okay? Because it has to be the positive numbers only, so no zeros, right? Consisting of all vectors x and the y, so that's x, that's y, in R2 such that x is greater or equal to 0 and y is greater or equal to 0, obviously, because it's positive, okay? Now, is this a subspace or is it not? Can anyone